So recall that we can write e to the x as the following Taylor series xi over I factorial. You may recall this from calculus class when you first learned about Taylor series, approximation, and power series. And also note that if you want to approximate e to the x, you often do so in a finitely truncated Taylor series. That is, we express it as follows. It's approximately equal to t sub n of x, where that function is defined as the sum from I equals 0 to n of x to the I over I equals, over I factorial, not I equals 0. Okay. Now, in numerical analysis, when we're often analyzing the error of our methods, we use two different types of error calculations. We use either absolute error or relative error. Relative error tends to be a lot more useful, and we can define the relative error of a approximation of the exponential function as follows. So the absolute value of the difference of our true value and our approximate value over our absolute value of our true value. Now, it would be very helpful to know what the upper bound for this relative error is. In other words, we want to know how off our approximation can be at most, given some n. Now, so we could actually come up with an expression for this. So let's assume this expression only works when x is greater than 0. We'll see why. Let x be greater than 0. Thus, we have the following. Oh, sorry. I should write this differently. Let's just let x be greater than 0 for now. Now, if we want to find an upper bound for the relative error, a good starting point would be to compute this term here. And we can do that easily. We have definitions for them right here. These two lines, we already have definitions for them. So let's just compute the difference of them. So e to the x minus t sub n is equal to I equals 0 to infinity xi over I factorial minus, I'll use j here, just to make sure we don't get confused. J equals 0 to n xj, j factorial. Okay. But what can we know here? These n terms in this sum are all already in this sum. So all this difference really is the sum from n plus 1 to infinity of xi I factorial. Right? We're just removing those terms from that power series. It's still, the result is still a power series, but we're just starting at n plus 1 now. Okay. So now, plugging this into our definition of relative error, we have r sub n is equal to the absolute value of the power series from I equals n plus 1 to infinity of xi I factorial over e to the x. Cool. Now, there's one thing we can note about this term in the numerator. we can actually pull out a common factor of x n plus 1 over n plus 1 factorial. And you'll see why this will be helpful in a second. So let's pull out that common factor. It'll still be within the absolute value. X n plus 1, n plus 1 factorial. And then we're going to have times 1 plus the absolute value of 1 plus bx over n plus 2. Right? So we have this term, then the next term after this, after x to the n plus 1 over n plus 1 factorial, would be x to the n plus 2 over n plus 2 factorial. So we're just removing the n plus 1 factorial from n plus 2 factorial, and all that we're left with is n plus 2. And we continue this process. This would be n plus 2 times n plus 3, and so on, right? And when we continue this, we can get the following. Now, what can we notice about this term in the numerator? Well, we can actually recall that we have the following. So for a1 plus dot 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 plus an, if this sum is less than or equal to the absolute value of a1 plus dot 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 plus the absolute value of an. And this is always true. So we can use this to go to our next step. So, whoops, this will now be less than or equal to. And it's okay, right? We can change to less than or equal to because we just want an upper bound for our relative error. We don't want an exact value for it. That'd be silly. That would insinuate that our relative error will always be the same, which is not the case. Okay. Now, all right, since the absolute value of 1 is just 1, oh, this should be a parenthesis. Absolute value, so 1 plus absolute value of x, n plus 2, plus the absolute value of x squared over n plus 2, n plus 3, and so on. All of this over e to the x absolute value of that. Now note, we're dealing with less than or equal to here. We can, with free will, just remove these denominator terms, or change them rather. So if we change this n plus 2 to 1, for example, we have this. We have that x over n plus 2 will always be less than or equal to the absolute value of x. Or in the case, well, I guess this would be in the case where I mean, x could be 0, I suppose. I guess that'd be the one case here, since n must be positive. But I mean, we are assuming actually that this is a bad example. We're assuming that x is greater than 0, but generally we have this, and we'll keep the less than or equal to here since we assumed that it's less than or equal to this equality here. Okay, so let's do this on the next page. So given this fact, we can change those denominator terms to terms that are smaller than the ones given here, and the result will be that this current Rn is less than or equal to our new sum. So let us go to the next page. So this means that we have Rn is less than or equal to, wait, I have that, okay. Thought I forgot to write something. X n plus 1 over n plus 1 factorial times 1 plus the absolute value of x plus the absolute value of, whoops, the absolute value of x squared, 2 factorial, and so on and so forth. So this 2 factorial in our x squared term, when we go back here, this 2 factorial must be smaller than this. It has to be. Even if n is 0, this will still be 6, and n can't be 0. So no matter what, it'll be smaller. So we know that Rn must be smaller than this term here, than this numerator. And since the numerator we want to keep Rn less than or equal to, we need to make that numerator. We need to keep that numerator larger. We can make the numerator as large as we want at this point, as long as it's larger than the term we currently have there. And we know that Rn will be smaller than that. And we have our absolute value of the x there. But remember, x is greater than 0. We have one more step before I get to that point. So we have, let's move this down a little bit. So we have Rn is equal to the value of x plus n plus 1 factorial. And then, what is this though? Well, that's exactly just the Taylor series of e to the absolute value of x. So this is times e to the absolute value of x over the absolute value to the x. Also, recall, we assumed that x is larger than 0. So we know that the absolute value of e to the x is equal to the absolute value of, e to the absolute value of x, since we have x is greater than 0. You can check this for yourself. It's quite intuitive though. So, because, yeah, I mean, the absolute value of e to the x will always be equal to the e raised to the absolute value of x when x is greater than 0. You could check that. You could check this graphically if you'd like. It's probably the best way. Or you could just intuitively think about it. So with this fact, we now have that Rn, since these two will cancel, we have that Rn is equal to x n plus 1 for n plus 1 factorial. Absolute value. Not equal, less than or equal to. And now we have an upper bound for our relative error for our Taylor series approximation for e. As long as x is greater than 0, we know what the relative error must be smaller than or equal to. We know what it must be. We know what its largest possible value. It can be smaller, but it cannot be larger than this bound here. So that's a nice little proof. In the next video, I'm going to discuss how we can approximate some sort of bound that we use machine epsilon with. In other words, we want to find some sort of bound to keep our relative error smaller than machine epsilon. I'll discuss that in the next video. Thank you all for watching, and I hope you enjoyed my first numerical methods video.